Hello. Let's talk pendula. And in particular, let's talk energy transformations while a pendulum swings. All right. What I've done here to illustrate the point we need to illustrate is I've made graphs, bar graphs, which we don't do a lot of bar graphing, but they can be useful in this context. Graphs of energy, of different forms of energy, for three different instants while this pendulum swings. We've got a first instant where this object is released from rest, instant 1. We've got instant 2 when it's swinging on the way down, and instant 3 as this pendulum swings through the bottom of its arc. Now let's define this height as height 0. That's a convenient thing to do. It doesn't have to be there, but that's a convenient place to call height 0. And, well, you'll notice that what I've defined also up here is an amount of gravitational potential energy that the Earth pendulum system has at instant 1. You know, the instant after this thing is released, or as it's just being released. Now, the other thing that we should talk about is our x-axis here. Notice we have this, well, we know K is kinetic energy. We know UG is gravitational potential energy. And now we have, is that it? And now we have what I'm abbreviating ME. And ME for us stands for mechanical energy, which by definition is the sum of these two energies. All right? So, in the simplest case, since, well, in instant 1, if we're released from rest, that means K is 0. At instant 1, we have this much UG, and that means that, let me see, watch this, infinite counter. That means that since there's 0 K, and ME is the sum of U and K, then that's how much mechanical energy there is. All right, now, what the heck else do we know for any other instance? Well, the ideal case that you were able to, or the ideal conclusion you were able to draw from the lab that we did was that, well, we didn't really even look at instant 2, right? We just looked at, kind of this instant here and this instant here. What you should have been able to conclude is that, again, allowing for some imperfect, practice, allowing for some imperfect raising of the object to just the right height, or some factors that are beyond our control, what you're really supposed to see is that there's, that there is a constant amount, or that there was as much mechanical energy at the bottom as there was at the top. And really what happens is, the big deal is there's the same amount of mechanical energy at any instant. We don't have a great way, we could find a way to measure forms of mechanical energy, to measure U, to measure K during instant 2, but it's a little bit of it's just procedurally more challenging to get the photo gate timer lined up just right. So we compared 1 and 3, but what we need to be able to do is generalize and say really at any instant there's the same amount of mechanical energy. There's the same sum of K and U at any and every instant. All right, now, how much K or U are there at different instants? One of them is a little bit easier to define, and that comes from our choice of height 3 being 0, and that means that there's absolutely no gravitational potential energy at that instant. And that means at instant 3 here at the bottom, if, again, mechanical energy is the sum of equals the sum of K and U, this must mean that, well, if U is 0, similar to how K was 0 here, this means that all the energy in instant 3 is of the form K. And this is the most common thing to maybe initially state, is that, well, all the U, all the gravitational potential energy turns into kinetic energy. Well, maybe it does, but again, that depends quite a bit on if you call that bottom height 0. Right? You don't have to call that bottom height 0 But the big takeaway is that no matter what, no matter where you call height 0, this is the big takeaway, that this energy and this energy and this energy and comparing this to this, or any of these mechanical energies compared to each other, have to always be the same. Now, have to is, we got to qualify that, but the big deal here is that mechanical energy is constant. There exists a constant amount of, maybe you say total, mechanical energy. All right? What can happen is that kinetic energy can convert into U, G, or UG can convert into K. Or maybe like in instant 3, I need a new color here. No, I guess I'll just do green. What might happen, you know, how far down is this? I mean, quite literally, check it out. As compared to this height, right? Here's height 1. I mean, here's height 2. Here's height 3. I mean, it looks to me like height 2 is about a, right? There's like 1, 2, 3. Like maybe height 3 is, say, like a third of height 1. Height 2 is like a third of height 1. That would say that there's reasonably maybe like a third as much UG here as there is at instant 1. Well, so there's like a reasonable bar graph for UG for instant 2, and that means that the rest of it, the other 2/3 of the energy, must be of the form K. Yeah? Fair enough? So ME is constant, and I'll even say at any / every instant. There's a total amount of the sum of K and U at any instant. Or really, we're going to say here that mechanical energy is conserved. So if things worked out, you know, quote unquote, well in the lab that you did, you should see fairly similar amounts of mechanical energy at your initial instant and your final instant. Now, they're probably not exactly the same, and they kind of actually shouldn't be. We're going to talk about why that is, but you should see that they're pretty close. And for some of you, they won't be, and that's because you're a person and you goofed up. People goof up. All right, it's hard to do labs exactly right, especially with, you know, these almost infinitely adjustable pendulums that we're using. But the idea is, you know, part of drawing a conclusion is saying, even though my data is not perfect, you know, can I feel pretty good about stating something, you know, maybe assuming that I can explain away why there are small differences, or maybe it makes sense that the final energy is actually different from the initial in the way that it is, but maybe I can, you know, neglect that, think about what could have caused that, and say, well, if that wasn't there, you know, could things have been equal? It's hard to write a good conclusion, especially in the face of, you know, real world data. But this is, you know, really needs to be ours, that for a system like this, again, with a certain assumption we're going to get to in a minute, we can say that mechanical energy is conserved. All right, and so let's try to apply that. We're going to apply that in a real question about a pendulum. So a pendulum is raised to 35 centimeters above the tabletop. What's the speed when it's at the bottom being 5 centimeters above the tabletop? So here's what we're calling the table, and we're calling that maybe height 0, and this is height 5 centimeters, and this is height 35 centimeters. Now, we're going to apply conservation of mechanical energy, and here's how we do it. That means that at any two instants that we can arbitrarily call initial and final, that there's a total amount of mechanical energy that's the same. All right? By definition, mechanical energy, is the sum. Is the sum of K and U These, you. So K initial plus UG initial. That's ME initial. K final plus, oh man, the whole eraser thing is just the worst. Plus UG final. There's our final mechanical energy. A couple of choices here, all right, is you might at this stage say to yourself, all right, when and where are any of these quite literally equal to 0? Well, I'm going to say this one is equal to 0 because, assuming we're calling this our initial instant and that our final, our initial velocity is 0. You know, this assumes, it doesn't say, I probably should have said and released, as opposed to and, you know, thrown downward from there. All right. Now, right now we don't have a final height of 0, but you know what we can do? Let's just say these heights are given relative to the tabletop, but if I feel like it, I can change where that 0 height is, and we're still okay. All right, I'll show you why that is in a minute. So let's just say now, again, we want the speed at the bottom. Well, speed lives in here. So now's the stage where we start saying, like, well, UG is mgh, and K is 1/2 mv squared. And this UG is mgh, right? So this turns into this turns into this turns into that. We're starting to write detailed expressions for all of our energy terms. Now, what else happens? I want you to notice, look at this. In every one of these terms, there is a common factor of m, which means we can divide every term by m, and this factor of m divides out of every term. So it actually doesn't matter what the mass of the pendulum is when we're trying to find speed. This is the thing we're trying to find. It certainly, I mean, the amount of mass certainly matters if we want to know how much energy there is, but this question is, what's the speed of the object? So we actually, those masses were very, very welcome to divide away. All right, I want to get this V by itself, so I got to get this stuff out of there, subtract it from both sides. We get GH initial minus GH final is 1/2 V final squared. Now I'll do this, multiply both sides by 2, the whole side. And you know what I'm going to do? Watch this. I'm going to factor out this G to leave us with that. Now that would be VF squared. I'm going to say there's our expression for VF. All right, now here's what's interesting. Watch. We can either do 35 minus 5, that gives us 30, or we can do 30 minus 0, that gives us 30 also. All right, so the point there is it doesn't matter where you call 0, and you can adjust if you feel like it, right? It's more convenient for me to call this height 0, and what I really probably would have done is, by calling the final height 0, I would have gotten rid of this whole term. I would have gotten rid of this whole term. I wouldn't have even had to have done this. And those could be gone. And we just end up with this expression, as long as our initial height is measured relative to our final height. All right, so that's going to be 2 times. Now here, what do we use for G? I'm going to use 10 because it's not wrong. It's approximate, but it's not wrong. And, well, now watch this. 30 centimeters. I do have to do 0.30. Can you move? Can you move, please? Can you go? There you go. 0.30 meters. I do need my heights in meters if I want my final velocity to come out in meters per second. So 20 times 0.3, that's 6. The square root of 6. The square root of, I shouldn't have done that. The square root of 6 is, you know, what's the square root of 6? It's like 2.5. 2.5 is 6.25. Let's call it 2.4-ish. You can solve in more There's your answer. You might even recognize it. Oh yeah, you know what? We actually dropped a pendulum from around that height, and yeah, that was maybe around the speed that it got to. Yep, that's it. And you know what doesn't matter at all? Doesn't matter how long this thing is. I mean, all that matters is difference in heights, difference in speeds. All right, so that's a pretty exhaustive solution for one of these, what we call conservation of mechanical energy questions or problems. Okay? Okay. Now, there are lots of situations in which conservation of mechanical energy can be applied. And here's a big deal, all right? We got to assume something here. And we have to assume a nice perfect case, a nice perfect, lovely utopian physical world where there's no friction, no air resistance, which some of you will refer to as wind resistance, but it doesn't need to be windy for air to get in the way of things, all right? And, you know, the presence of these things still allows energy, like all total universe energy, to be conserved, but not just the simple mechanical only kind of energy to be conserved. So the right kind of question will say things like neglect friction and air resistance, or neglect frictional losses, or stuff like that. All right. So when can we use mechanical energy conservation? Well, lots of cases where K turns into U, or U turns into K, or, you know, basically where, you know, speed turns into height, or height turns into speed. And let's assume there's no friction and stuff. So when's that? Well, one of them is certainly the pendulum. And again, assuming that ideally the pendulum is in a vacuum. I don't know. There's no air in the room somehow. Sure there is, but let's neglect what the air does. All right, that's a big one. Plain old, what I call, or what anyone that does physics stuff calls free fall. Just drop something, all right? And not only that, you could drop something, or throw something upward. Even if we throw something upward with an initial speed and it gets to a certain other height with a different speed, right? We're changing speed for height. We can apply conservation of mechanical energy. Again, as long as we assume that friction isn't doing a whole bunch of bad stuff for us. And you know, a third one for sure, a very common one you'll see is like, I don't know, how about a roller coaster type situation, right? At one instant higher up and slower, at a different instant lower and faster. Okay? I mean, the simplest roller coaster is just a hill, right? Here's a certain speed, here's a faster speed. More K but less U. All right? Those are three big ones. Oh, you know what? Free fall? Free fall can also just mean any sort of, projectile motion, where an object moves not just up and down, but in two dimensions, continuously changing height and therefore continuously changing speed. All right, so here's a roller coaster, real kind of general drawing. You know, and we've got like an initial instant v. I'm saying here's initial over here, and here's final over here. So let's say, what's the speed now? Well, it depends on things like, you know, what I would probably right off the bat do is say, all right, well, I'm going to call this height 0. It's the lowest height. That's the most convenient place to call height 0. And this is height initial relative to there. Now this is different than our kind of standard pendulum question where we take the thing and release it from rest and it starts to swing. We are actually saying that this roller coaster car, or that we're treating as a little point mass here, we're saying that it does have an initial speed. It's going up this hill at a certain speed. And notice, this doesn't have to be like, yeah, it doesn't have to be at the top. Uh-oh. It doesn't have to be at the top and the bottom. It's just at any generic instance. Like, oh. So at any two instance, again, nothing about top and bottom. Doesn't have to be at a lowest place. You know, we can just compare. We can compare mechanical energies really by saying they're the same. All right? And again, a good question will say something like, neglect frictional losses. Assume there's no friction. A frictionless track. Right? Those aren't real assumptions, but they make these investigations quite a bit easier. So then, you know, the typical next step is to say in whatever you want, in whatever order you want, K and U, it could be U and then K, equals K final plus U final. And then you ask yourself, are any of these terms 0? Well, this is not a K initial is 0 because look, this thing is moving. This arrow represents this thing's speed at the beginning. So K initial is not 0, UG initial is not 0. But look, we've chosen H final is 0, so we can say that's gone. Right? I might, if I were you, say, remember, because H final is 0, therefore U is 0. And then I go to this stage. Typically, I say, all right, this is 1/2 mv initial squared. This is mgh initial. This is 1/2 mv final squared. Right? And we're trying to write an expression for final velocity. Notice again that we have a common factor of m in every term. That means we can divide every term by the same factor, and those in effect divide away. I prefer to say divide away to cancel. We want v final, so we just take everything and multiply by 2. And if I distribute that 2 through here, I get 2 times 1/2. So I just get v initial squared. And then I get 2 times gh initial. That would be vf squared. So there's vf for this situation. Right? So things, you know, these expressions will change, you know, certainly depending on what you're trying to express. If we're expressing a height, then it's not going to look like this. You know, there might be a minus in here depending on, you know, difference if the later height is higher up, or, you know, if you start, there's different situations. And I'm not saying like this is the thing to remember. This is a specific application of, well, the thing to remember is this. This is our approach to solving a whole bunch of problems, right? That can look quite a bit different, right? There can be lots of different scenarios in which this is happening, so we can apply a really, really important idea, right? That mechanical energy is conserved. Again, assuming that we simplify our world, which, as you'll see, a lot of questions do. Okay? Okay. I think that's it for today. See you soon.